Hello, I hope the screen is visible. So, so I'm Paul Biswas. I am a PhD student and emeritus scholar at IIT Bombay. I take these weekly tutorial sessions for this course. And today is week 3. Uh, Today we will get get into a little bit more depth about uh, about these deep learning neural networks in general, right? So we'll talk about activation functions and loss functions and things of that nature, and what is appropriate, what kind of activation functions and loss functions are appropriate for what kind of applications, right? And we will see some example questions, and then at the end I intend to also kind of break down all of uh, the math that goes into like a simple neural network, right? Like a fully connected uh, fully connected two layer, one hidden layer neural network, right? how how that processes the information, how it learns the optimal parameters, right? Through gradient descent. So we'll kind of uh, go through the math of that a bit, so that you have a basic understanding of how things happen, right? So yeah, so without further ado, let's start. So here is a description of a fully connected neural network. There are two hidden layers. Um, there's one input layer, two hidden layers, and output layer, and each hidden layer. So each layer basically has two states corresponding to it, right? One is the pre-activation, which is uh, the raw output of the weight multiplication and the bias addition, right? And the other part is the post-activation, which is after applying the activation function, right? So here, obviously, because there are two hidden layers, you'll have three sets of weights and three sets of biases, right? And yeah, it goes like this, right? And the question here is very simple. So pre-activation layer values at layer I. So how do you describe them is the question, right? Which is should be very simple based on what you have seen in the course, as well as even this diagram is kind of making itself evident what is happening. So as usual, I will give a little bit of time for everyone to answer it, and you can mention it in the chat your answer, and in a minute or so I'll continue. Rather, I will explain the answer and then we will continue to the next question. Uh, uh, yeah, so as I said, it's should be fairly straightforward, right? The pre-activation values are basically the weighted sum of inputs coming from the previous layer. Right? So at layer I, the pre-activation is the weighted sum coming from the layer I minus 1, right? And the bias is also added there. but that's fine. Uh, Rather, the bias is it depends. No, the bias is also added there. Right? So here it's actually not just the weighted sum, but also including the bias, right? Uh, which can often the which can often be expressed simply by extending the vector of neural activations by one, right? So we just extend the vector by one and then multiply by a larger value, larger matrix, which also includes the biases. So that is also one way of doing it. Right. So let's move on. So this is about dimension matching, and specifically it is about matrix multiplication and dimension matching. For matrix multiplication, so A1, which is the pre-activation in the first hidden layer, can be written as W1x plus B1, right? Obviously. And we are considering vectors here that are expressed as column vectors, right? Which means that they have a number of rows and then one single column. Question is simply what is the dimensionality of the weight matrix, given that the input layer has 6 inputs and the first hidden layer has 9 neurons. Let's see, 6. Yeah, so this is also again correct answer. It is the dimensionality of the weight matrix is 9 6, right? And you can work it out. Start with the fact that x is given to be a column vector, which is also evident based on the way the equation has been written, right? Obviously, because w1x is a matrix vector product, and the output should also be a vector of the same like the same orientation, right? It is, if it is column vector, it should be column vector. If it is a row, then it should be something like that, right? So you apply w1x for matrix multiplication. uh, the number of the number of columns of w1 should match the number of rows of x, right? That is how you do matrix multiplication. And for that to be the case, then the number of columns of w1 obviously should be 6, and the output should have the same dimensionality as the hidden layer, which is say, which is given to have 9 neurons, which means that the number of rows of w1 should be 9, right? So you apply w1 9 comma 6. This is the shape of the matrix, multiplied by x, which is 6 comma 1, because it is a column vector, and then you get a1, which is 9 comma 1, right? This 6 in the 6 part in the middle, they get consumed, because that's how matrix vector products happen, right? You can think of that as these dot products of the dot product between the row of the weight matrix and the column vector, right? So you get this part gets absorbed into it. That is one way of looking of thinking about matrix multiplication, right? So yeah, 9 6 like I said. Now we will kind of flip this a little bit, and instead of considering column vectors, we'll now consider the input and everything else as row vectors, which is also something which is you can something you can obviously do, right? uh, it it's entirely up to you to specify how you want to treat your uh, vectors, right? So if we consider them as row vectors, then write the equation a little bit differently, uh, as you can see over here. And the question remains the same: what is the dimensions of w1, right? So once again, you a little bit thought, this should be fairly straightforward given the information and the discussion of the previous question, right? So yes, should be able to answer it pretty easily. So yeah, obviously in this case, right, you take when you treated them as column vectors, you got one answer. And if you treat them as row vectors, then obviously it will just be the flip version of that, right? So in the previous question, you got 9 comma 6 as the dimension of the weight matrix. Now here, it will simply be 6 comma 9, right? And once again, you can just write it, right? You can just write x times w, where this x and a are row vectors, and that just becomes 1 comma 6, and then you multiply it by 6 comma 9, then you get 1 comma 9, right? Which is like row vector with 9 values, right? Which is what you want. Uh, so here, obviously, as you have noticed, the pre-activation values go into this thing called as activation functions, right? And the choice of the activation function is the first uh, engineering choice that you have to make your networks work, right? To make them run. And the choice of activation functions has to be done kind of carefully based on what is the kind of output that you want, and this is especially for the final layer, right? So the activation function for the final layer has to be chosen kind of carefully based on what you want the network to actually have, right? So we'll consider some activation functions. This is the sigmoid function, which we had discussed in the previous session as well, right? So this should be very familiar to everyone, the sigmoid function. The question is, consider a task where the output is a probability distribution, right? So as the output, let's say you want to get the probability distribution of a certain item being present, right? You give it in the inputs. And the question is the sigmoid function a preferable kind of output, if not one, right? So you can just answer the first part, and we'll anyways talk about why it is not preferable for a situation like this, right? Uh, Important point to note here is that I'm talking about the final layer activation functions. You can very well use sigmoid in the inside, like in the hidden layers, even in this kind of a problem, right? Or generally any kind of problem. Uh, but of course, even there are some issues with using sigmoid, but we will not get into that. Those issues, right? I mean, they have they have they have to do with uh, gradient of the function. Okay, okay. So I will just explain the answer and the solution for this problem. Uh, so the given question is, consider a task where the output is a probability distribution function, right? And we have to keep in mind the characteristics, right? The properties of a probability distribution function. And then the important property in this point is, basically probability distribution functions have two important properties. One is that every value should represent a valid probability, which means that the value must be non-negative. Uh, it should be less than one, right? The values of the probabilities, probability distribution functions must represent valid probabilities, and in this case, obviously, we are looking at discrete functions. We are not looking at continuous probability distribution functions, right? So basically, the values have to lie between 0 and 1, which is satisfied by sigmoid, right? Sigmoid values always lie between 0 and 1, but there is a second property of probability distribution functions, which is that all of the probability values should add up to 1, right? And this is something that sigmoid does not satisfy by default, right? So it is not a property that sigmoid function uh, is kind of built to satisfy, right? So yeah, so the sum of output values should be 1. That is a property where this activation function actually fails. So knowing that we cannot or we do not use sigmoid activation functions, what do we use, right? So given that the target output is a probability distribution function, what is the preferred activation and loss function to use, right? So you have a bunch of options with different combinations of the activation function and the loss. And the question basically is just asking you what is the most optimal choice, what is the best choice that you can make, right? So I'll give some time for you to kind of work it out, and you can share your answer in the chat, and in a couple of minutes I will discuss the solution to this, right? And, looks like one has answered. Just right. So this is a fairly straightforward setup, right? This I think this should have been covered in the classes. Uh, but yeah, so the main thing here is that the target is the probability distribution function, right? Which means that the activation function should generate something that is normalized in a sense, right? So the output of the activation function should satisfy those properties of probability distribution functions, specifically in just the two properties that I talked about earlier, right? That is that every output should be non-negative, and that every and that the sum of all the outputs should be one, right? And out of these functions, you can basically remove the functions that doesn't satisfy these properties, right? So sigmoid function we discussed earlier does not satisfy the second property, right? It satisfies the first property but not the second. Tanh function satisfies neither property, because tan h function, if you know, it goes from -1 to 1, so it generates negative outputs as well, which is not a valid probability, right? So discount the tan h, which are we are just left with then the softmax function, which does indeed satisfy the property that we want, right? So softmax function, we'll see how it is defined in a moment, and much later after we are done with discussing all of these example questions. I will go through a little bit more detail about the softmax function in association with cross entropy loss, and how you compute the gradients for that, things like that, right? So softmax function is one function that does generate probability functions as the output, and the most appropriate loss to use for it is the cross entropy loss, right? So this is a loss that is coming from that field of statistics, and it computes the distance between two probability distribution functions, right? And generates, so it computes the distance in a sophisticated way, but at the same time, it also generates very simple gradients that you need to uh, backpropagate, right? So it has best of both worlds in a sense, which is also something we will see later. So yeah, like I said, uh, you can discount all of this. Values don't add to 1, values don't add to 1. Squared error is inefficient for probability distribution, right? Because it treats functions as kind of generic functions and tries to minimize the distance between those functions, but they are not generic functions, right? So these are probability distribution functions. They have a very specific kind of target shape that they want to achieve, right? Specifically for classification, you just peak at one point, which is the correct class, and then you're zero everywhere else, right? And for those kind of things, cross entropy is the best kind of loss. And here, so yeah, so like I said, we'll see what these functions are as well, right? So you can appreciate why they satisfy all of these properties. First of all is the softmax function, where you'll obviously apply the softmax function on top of a set of pre-activations, right? And in our convention, we have used uh, small a for pre-activations, right? So we say softmax of small a L, where capital L represents the last layer, final output layer. Softmax of AL is basically nothing but AL e to the power AL of I divided by sum over e to the power alj, right? Which basically you are adding up all of the numerator terms and normalizing it, normalizing them by this value, right? Which gives you basically normalized output, right? From so that the sum of every all of the outputs is is one, and the reason you use this e to the power ali is so that you have all non-negative outputs, right? Because exponent of anything, any number is always positive. uh, so you always get non-negative outputs, you always get outputs that sum up to 1, right? Values add up to 1, values are non-negative. And the other part is the cross entropy loss, which is simply defined like this, right? So you take yt, which is the target. So you take yti, multiply by log yi, which is log y is the output that you get from your network. Uh, Rather, y is the output that you get from the network. So you multiply yti by log of yi, and you add it up with a minus sign, right? And this is derived from uh, entropy definition from information theory. The information of an event is defined as information of an event x that happens with the probability of px is defined as negative log px, right? So the more unlikely an event is, right, that is, the lower this value of px, the higher the level of information that is present uh, by that event token, right? So this is basically stating in a simple form uh, a kind of result from information theory, which is kind of which is also used in this loss formulation, right? So if we consider a problem where uh, an output layer has to predict xy coordinates, but there is a restriction on it, right? So here we have to predict xy coordinates of a point with a constraint that they must lie within a given range, right? So x must lie within 0 to 2, y must lie within 0 to 2, right? So the points are constrained within this box in xy. So here the question is the same again. What are the activation and loss functions that we can use? Like what would be the better ones to use? And once again, I will give some time for people to work it out, and then we'll discuss the solution. uh, so this is obviously a little different compared to the previous problem, right? first of all, obviously, the kind of the output that we want is a little different. We don't want probability distribution functions anymore. We want xy coordinates, right? And you know, the value of these xy coordinates is kind of freely allowed to vary, but given within some constraints, right? Which means that for the loss, we don't we are not going to use cross entropy anymore, right? Obviously, right? Because cross entropy is a very specialized kind of loss that does a very specific thing, right? Which is specifically it optimizes, the output probabilities uh, for a classification problem. And this is obviously a regression problem, right? So we don't use serial loss, right? So what is the other alternative? The other alternative here is squared error loss, which is obviously the one that we are going to use, right? So squared error loss will fit well within this problem. The only thing left to determine is what should the activation function be, right? And generally for this kind of a regression problem, the activation function would be linear function, right? But linear as is to say that there should be no activation function at all, right? So you just whatever output you get from your reactivation, that is itself passed on as the final output, right? But here I have imposed a condition, right, which is that I have imposed a constraint here, and this kind of changes things a little bit, because now that we are constrained, we can look into activation functions that are also constrained, right? So we can look into sigmoid and tanh activation functions, which are constrained, and you can use those instead, right? Because they will, by definition, give values that are bounded uh, between 2 points, right? So sigmoid will give values that are bounded between 0 and 1. Tanh will give values that are bounded between -1 and 1, right? And then you can simply transform them in some easy way, so that they match the boundary imposed by the problem, right? So the sigmoid output, you can simply multiply it by 2. You'd get something that is bounded within 0 to 2. And for the tanh output, you can just add 1 to it, and you'll get something that matches the constraints given by the problem, right? So because this is a special case that is hooked up to add some sort of constraint in the output, in the regression output, we'll no longer use the linear or no activation function kind of setup. Instead, we will use sigmoid or tanh, right? And yeah, so the reasoning, whatever I outlined, obviously C loss is unsuited, linear is unbounded, right? It does not have any bounds, and you cannot use softmax, obviously, because softmax, essentially, if you have two outputs and you apply softmax on it, it will force your outputs to to lie in this line of x plus y equals to 1, right? Because softmax always ensures that the sum of all the outputs is 1. And so in this case, you have two outputs, x and y. It will force them to uh, follow this line, right? Which is again something that you probably do not want, right? Because you might want to explore the entire uh, area that is available to you. Right. And like I said, the bounded activation functions, you can either apply uh, simple transformations to the output, or you can apply simple transformations to the target, right? You can scale the target by 0.5 to match it with the sigmoid output, and you can shift the target by -1 to match it with tanh, right? So that's something. excuse me, output layer. uh, yeah, so this is again continuation of the same type of problems, the same type of questions, right? But these are obviously, even though there are slight variations, and you can appreciate the differences in, what you want, what you need, right? For the different types of scenarios that you might encounter. So here are basically two setups. One uses linear, right? And you have a loss that is mean squared error loss. The other one is generating a softmax output, right? And you have a loss that is the cross entropy loss, right? So this is softmax plus cross entropy. This is linear plus mean squared error. And the question here is, which of the statements regarding these two setups is true. Number one, A is that number one is suitable for real number targets. Two is that B, two is suitable for real number. Which one is suitable for real number? Uh, Gradient of L with respect to AL takes the same form for 1 and 2 if expressed as a function of y, or gradient of L with respect to y takes the same form for 1 and 2 if expressed as a function of AL, right? So I think the first part, that is options A and B, are fairly straightforward. Option C and D, so here is something a little bit tricky going on here, uh, which which you can only appreciate if you actually perform uh, the, the 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 gradient differentiation step for both of these scenarios. Obviously, for option one, the gradient is very simple, right? You just have this square error, which is a very simple function to differentiate. You differentiate that and get your output. There is not even any activation function that is applied, right? So the gradient with respect to the output is the same as the gradient with respect to the reactivation AL, right? The major question arises when you try to differentiate this, right? And that is something I intend to cover after going through all of these questions. So this is one. Uh, so this question will be, like, this part of the question will be covered in more detail at the after finishing all of the question setups, right? So once again, I will give some time for people to work this out, or at least try to work it out. And in a couple of minutes, I will explain briefly, and then later I will explain in more detail. Okay, so like I said uh, earlier, obviously the first part of this is fairly straightforward, right? Obviously, option one is, or rather, the setup one is the one that is suitable for a real number of targets, right? Because you are applying linear output, which is unbounded, like real numbers are unbounded, and then the loss is squared error loss, which fits well within a regression problem, right? So that is fairly straightforward. The other part is that, so here is a kind of little bit tricky thing. So the gradient of the loss with respect to the uh, reactivation, right, is the has the same form in both of this, which is a non-trivial kind of result that you would never, that you would normally not expect, right? Because if you think about it, if you just look at these functions, right, the first one is fairly simple. In fact, there is no activation function uh, applied even, right? And then you have a very simple square differentiate square error loss, whereas the second one we're applying this complicated, softmax function. You're applying this loss function that you know has this. So the other, so they here there is a little detail that is not mentioned. So here the detail that is not mentioned is that these target values must take this one hot notation, right? So specifically you are applying this softmax cross entropy for a classification problem, which is where softmax cross entropy is basically always used, right, for classification problems. And in that case, very surprising result appears when you actually perform the differentiation step, is that when you take the gradient of of this loss, the cross entropy loss with respect to AL, which is the reactivation, you get a form that is exactly the same as what you would have gotten with this linear plus square error combination, right? And this is something I intend to cover uh, later. So we'll go through the differentiation step so that you can see how that emerges essentially. All right. Uh, Consider a single output network, right? So here, so in the previous cases, we had considered multiple output networks by default. Here we consider a single output network. So the output size is one, right? And it just outputs one value, right? And what it must output is the probability of an event, right? So the output has to be the probability of an event. The question is what should be the ideal activation in loss functions, right? So you have your options, the combinations, sigmoid function, loss, linear, squared error, softmax function, loss with something, yt log y, softmax function, loss with yt log y, 1 minus yt log 1 minus y, and so on and so forth, right? So this is uh, this is a kind of example. This is a kind of a setup where you are trying to predict whether uh, something has happened or not, and that something is just one instance, right? So it could be is that you are reading some document, right, and you are trying to predict whether the document is, whether the sentiment in the document is positive, right? So in that case, if it is positive sentiment, uh, you would return some value that is high, right? The probability of positive sentiment is high. If it is not positive sentiment, then you want to return some value that is low, right? The probability of positive sentiment is low, right? So you're returning some sort of probability of something, right? Just one thing, single probability value, right? So keep in mind those properties of probabilities and try to figure out which combination of activation and loss functions would be most suitable for this problem, right? Once again, I will give some time for you to work it out, and you can share your answer in the chat. Uh, okay. So let's see. Has anyone answered? Tried answering. Uh, sorry, I was at kick off for a couple of minutes. Uh, yeah. So we are considering here a single output network that must predict the probability of an event, right? So here the stipulations of probability distribution function are somewhat relaxed, obviously, because we are just predicting one single output, right? Which means that the only thing that we care about is that it should be a non-negative number and its value should lie from 0 to 1. And what is a function that perfectly satisfies that property? A sigmoid function is something that perfectly satisfies the property, right? So sigmoid generates a non-negative output. Sigmoid is bounded from 0 to 1. So obviously sigmoid is the correct option. The other part is concerns with the loss, right? And uh, since we are still dealing with probabilities, obviously we want to use something similar to the cross entropy loss. In fact, we would like to use an exact uh, an exact representation or an exact copy of the cross entropy loss, right? But now instead of having n uh, in objects that in like classification targets, for example, we just have one classification target, right? So we have uh, yt log y, right? But we also have to consider the inverse of that, right? Or the negation, rather the negation of y, right? So we also have to consider 1 minus y, the probability, and 1 minus y, the target, right? So this is nothing but the cross entropy loss, right? But instead of being generalized to n outputs, this is specific for one single probability value that you are outputting, right? So this is the cross entropy loss, and this is a sigmoid function, which will obviously generate a output y that matches with what you require, right? And as for the other options, we can uh, we can discount them quite easily. Uh, First of all, linear we cannot use because it is unbounded. Sigmoid function. Uh, so the problem with the sigmoid function is that it can get stuck in this situation where it defaults the output to 1, right? And if it defaults the output to 1, then your loss becomes 0, right? And it has found a shortcut way to kind of minimize the loss that could be problematic, right? So the way that you overcome that is by kind of taking care of the negation of 1 as well, right? So this first term deals with the probability that the event occurs. The second term deals with the probability that the event does not occur, right? It is the complement of the probability that the event occurs, right? So you divided your space into uh, these two options, and then you have to compute the cross entropy on both of these options, right? Because only then it becomes a valid probability distribution function, albeit is just one that has is one that just has two values, right? The probability of happening and the probability of something not happening, right? And single input, obviously single input softmax function is undefined because it will just default to 1, right? Because you are dividing by the normalized sum of the uh, constituent value elements. If there is just one element, you just get one every time. Right. So moving on. So here is this is the part that we want to do a little bit of deep dive uh, into a deep neural network, right? And we will deal with the very specific problem of classification, and we will only deal with the simplest deep learning model that you can consider, right? What is the simplest deep learning model that you can consider? The simplest deep learning model that you can consider is one where you just have a single hidden layer, right? If you don't have any hidden layers, then it becomes analogous to a perceptron problem, right? Or it becomes analogous to a linear regression or logistic regression kind of problem, and that is no longer a deep learning or deep neural network approach, right? That is something else. That is a linear classifier approach, right? And that is not something we want to do here. So this is specifically, like I said, the simplest deep neural network that you can construct. You have one hidden layer, you have one set of outputs, uh, two sets of weights, and you have two sets of biases, right? And to simplify it even further, we are even going to ignore the biases, right? So we are ignoring biases. So we can think of, you know, there are just two sets of weights. There are no biases. Uh, there is some reactivation with an activation function applied in a hidden layer. Then there is activation function applied in the final layer. In the hidden layer, to make things even more simpler, we apply the simplest kind of activation function that works. And this is not a bad choice. So this is something called as a ReLU, which is a reduce restricted linear unit, right? And basically it uh, it generates this output where if the input of the ReLU is greater than 0, then it just gives that as the output. The input is less than 0, then it gives 0 as the output, right? So it is the max of 0 comma x, where x is the input. All right. So this is a very simple uh, activation function for the hidden layer that is still non-linear, obviously, right? Uh, and then for the output layer, we apply softmax because that is what we are trying to do, right? We're trying to do classification, so we apply softmax, right? And so here are the equations that we care about for the forward pass, which is when you give some input and then the neural network processes it, and then you get some output, right? So first processing is a1 equals w1 times x0. So this is generates reactivation 1. Uh, next process is rather the next processing step is x1 equals ReLU of a1, where you generate the post activation function x1 and the hidden layer. Then third step is again weight multiplication. So a2 equals w2 times x1, right? And then final processing step is softmax, right? So you apply x2 equals softmax of a2, and that is your final classified output y equals x2. For regression example with MSE, we could have had x2 equals a2, y equals x2 equals a2. Right, we can write it as y equals x2 equals a2, and the loss would be simply the square error loss, right? But here, since we are doing classification, we are going to softmax and cross entropy, right? So then we come to the second important description, right? But the second part that we have to kind of define properly, right? And this the next part that we have to define basically is the label encoding, right? And here, let's say we are dealing with these handwritten letters, which is a very common kind of initial initial kind of example that you would try to test on, right? So the labels, or rather the target for classification, are typically encoded as what is called as one-hot vectors, right? Because so this is a multi-class classification problem. Multiple classes are possible, out of which only one is correct, right? So you will have a one. So in the label uh, of the class of the sample, right? In the label of the sample, you will have a one corresponding to the correct class, and you will have zeros everywhere, right? Because the probability, because the label is basically telling the probability of certain number being present, right? And the ground truth probability obviously is that with the probability with an absolute certainty, the probability of 1, we know that the number 4 is present in this image, and we are absolutely certain that no other number is present, right? So the probability of every other class is 0, and only the probability of 4 is 1, right? So this is the ground truth that we want to try to achieve. The other part here is deals with the loss, and I say loss, but it includes both the loss and the activation function. The loss obviously is the cross entropy loss, which is defined like this. This is something we have seen earlier, where you apply log on yi, right? And you multiply by the label, corresponding label target value, and you add it up with the negative sign, right? So you go through all of the classes and you add them, right? And I mean, this loss is kind of uh, it's not exactly intuitive exactly how this works, but one thing you can think about is you consider a situation of extreme wrongness, right? If your output was extremely wrong, which is to say that your output is very confidently predicting something that is not correct, right? So, for example, if you have a sample where 4 is there in the image and you expect a 1 at this 4 position and 0 everywhere else, but your network output is saying that no, there is a 9 there, and it is very confidently saying that there is a 9 there, which means that it has a very high value at this 9 position and it has very low values everywhere else. So you can imagine that the output has a 1 at 9 at this 9 position and it has zeros everywhere else. And you can try to figure out what the loss will be in that condition, right? So what will happen is that when you come to this 9 position, uh, you will have so rather when you come to this 4 position, right, where you expect the output to be 1, uh, but instead your model is very confidently wrong and it is saying that the probability of 4 being there is 0, right? So if we put 0 in here, log of 0 is negative infinity, and you get a very high value of the loss, right? Because at this 4th position you will apply apply your label, and your label will have a value of 1. Everywhere else your label has a value of 0. But if your output is saying that, is very confidently saying that 4 is not there, then you will have a very high loss that is being generated here. It's potentially, it's like tends towards infinite, right? So yeah, so that is one way you think about how this loss actually kind of works. So you think of situations where your network output could be like confidently wrong, very confidently wrong, and in those cases you will always see that the loss will be very high, right? Will be a high positive value. And the second part of it is the softmax function, which is, like we discussed, the activation function for this kind of classification problems. S of xi is nothing but e to the power of xi divided by summation over all of the classes e to the power of x point j equals 0 to classes. And like I said, this will ensure two things happen. Uh, First is that your outputs are normalized, in the sense that the sum of all of these values will be 1. And the second is that all of these are non-negative numbers, because e to the power anything is non-negative, right? So next part. So now that we have dealt with these forward definitions, the only thing remaining to do is the backward pass, right? So we need to compute uh, what is the gradient, right? What is uh, the backward pass equations, and how the gradient values are computed for the two layers, and from there you need to figure out what would be the update of the weights, right? So once you have figured out what are the updates that need to be applied to the weights, it's all done. Right? So you have a complete understanding of how this network would learn, basically, right? So in this case, this very simple example, there are only two layers for which we have to compute the gradients, right? First, of course, we'll have to compute the gradient for the output layer, and so this is a little bit tricky. Like I said, uh, we'll go through it step by step, right? So the loss is given by this, right? So the loss is given by negative log of x2 of I summation over I multiplied by label of I, right? So first step we do is compute the gradient of the loss with respect to x2 I, right? Which is x2, of course, is the post activation values, right? So you compute gradient of L partial. So these are all partial derivatives. So you compute gradient of L with respect to x2 of I. You get minus label I divided by x2 I, which is fairly straightforward, right? Because, you know, obviously we are taking the gradient with respect to x2 of I, the ith value, which means that all the other gradients, like all the other values, would be 0, right? Because they do not depend on x2. So you get minus label I divided by x2I, which is 1 by x is the gradient of log x, right? So you get this. So the next step here, so now that we have gradient with respect to x2, the next step is to get gradient with respect to a2, right? And remember that when you're doing forward computation, you're going step by step in this direction, right? Going from here to here, you get a1 x1 a2 x2, right? When you're doing backward computation, you're going in the reverse direction, right? So you compute gradient with respect to x2 first, and then you compute gradient with respect to a2, and then so on and so forth. So gradient with respect to a2 of I is, so here is no longer straightforward, because uh, if you notice the the softmax function, right, the output of the softmax at the ith position is not only dependent on the input, you know, on the pre-activation at the ith position, but rather it is dependent on the pre-activations at all positions, right? Because this softmax function is normalized, right? So because it is normalized, it is dependent on basically the pre-activations at all positions rather than just that specific position, right? So here, when you're trying to compute the gradient of L with respect to A2 of I, right, which is the ith term in uh, is the ith pre-activation term, then it's no longer just one single, but it's like the entire sum, right? So you add over all of the classes, all of the output classes, and you compute this chain rule term, right? So you compute gradient of L with respect to x2 of j multiplied by gradient of x2 of j with respect to a2 of I, right? So you computing this term, which is the same as over here, but for the jth element, and then you are seeing how does the softmax output of the jth element depend on the pre-activation of the ith element, right? So this is all that this equation is doing, right? And the way that you write these equations obviously is by using chain rule of uh, like chain rule of differentiation, right? Where if something is a if a function is a composition of multiple functions, then you just go one by the one after the other, compute gradients successively, and that's how you compute the final gradient, right? So we apply chain rule here, and we split it into two parts, right? So we split it in the case where I is equal to j, right? So the, the, the situation of pre-activation affecting its own not sigmoid softmax out, and we consider the situation where I is not equal to j, right? Which is that the reactivation of some other element affecting the softmax output of some other element, right? The reactivation of some element affecting the softmax output of some other element, right? So for the case I equals to j, we can basically get rid of this j. We just deal with I, right? So gradient of x2 with respect to gradient of a2, gradient of x2I with respect to gradient of a2I is just this, right? And this is just uh, the division rule of differentiation. You can which we just look into this, right? So we have something in the denominator, the summation over this e to the power xj, right? A summation over e to the power a2j, right? So squared of that, the denominator gets squared, and then in the numerator you get denominator value multiplied by the gradient of the numerator minus the numerator multiplied by the gradient of the denominator, right? That's how you do uh, that's how you do what do you call it? That's how you do this division term of division, like differentiation with division, right? When you have f by g, you do this, right? You apply, you get g square in the denominator, and then you get g gradient f g df minus f dg, something like that, right? So this is just that. And then if you simplify this numerator a little bit, essentially what you will get is is this term, right? You will get x2 of I multiplied by 1 minus x2 of I, right? 1 minus x2 of I is nothing but this e, uh, e to the power a2 of I divided by one of these things, right? So that is one factor. You can take this e to the power a2 of I common, and basically you get summation minus e to the power a2 of I, right? And then this e to the power a2 of I divided by one of these things is nothing but x2 of I. And then this summation minus e to the power a2 of I divided by one of these summations is nothing but 1 minus x2 of I, obviously, right? So this is a little bit of algebra, very basic algebra that you can do, that you should do, to kind of convince yourself that this is indeed the case. And then we'll move on to the other condition, which is when I is not equal to j, right? So we are looking at the situation where the pre-activation for some element is affecting the softmax of some other element, right? So here you are computing gradient of x to j with respect to gradient of a to with respect to a to I, and we apply basically the same rule again, right? So we apply the division rule. We get a square of this summation in the denominator, right? But in the numerator, because we are because we are taking gradient with different indices, right? Uh, we only get one term here, right? Because x2, the numerator of x2j depends only on a2 of j. It does not depend on a2 of I, right? So the gradient with respect to that numerator will become 0, which is the first term over here. The first term will be 0. The second term will survive, right? But the second term here is minus of e to the power a to I multiplied by e to the power a to j, which and then you divide it by the square of the summation, which you can simplify simply as x2 of I multiplied by x2 of j with a negative sign, right? So this is this is this part complete, right? So you have this part, you have this part now, and you also have gradient of loss with respect to x2y, which was a very simple um, setup equation. Now all we need to do is basically combine these three things, right, and write out this equation, right, which is the one that we have, that I have over here in the middle, right? So we combine these three equations, these three results, and we try to write this equation. So we get gradient of loss with respect to a to I is uh, is basically, so this has been split up into two terms. The first is a summation for j not equal to I, right? So this is the case where j is not I, j and I are not same, and you get label of j divided by x2 of j multiplied by x2I times x2j, right? And then separately you have the case where uh, I equals to j, right, which is what we have computed over here. You get label of I divided by x2I multiplied by x2I multiplied by 1 minus x2I, right? And then we combine these two summations and we build one single summation, which you'll get like this, right? So you get label j of label j times x2I minus label I, right? So yeah, so this label I times, so you cancel this x2I from the numerator and denominator, and then you multiply with this term, right? So you get label I times 1 and then minus label I times x2I, right? And this term can be plugged into this summation, and it will basically complete the summation, right? So it, instead of j at not equal to I, it will just go from j equals to 0 to n classes, this summation, right? And here, uh, this summation of label j times x to I. So here is the final trick. Basically, you are summing over label j and you're multiplying by x to I, right? So I is not changing, so you can take the x to I outside of the summation, and then you are just summing over label j, and you know that the sum over label j is always going to be 1, right? So you sum it over, you get 1. Finally, you are left with x to I minus label I, right? Which, if you think about it, it is, like I said, it is the exact same uh, form that you would get if you had used, if you were doing a regression problem with a mean square error loss, right? You would take mean square error between the target and the output. That should just be the square of the difference, and then you take gradient of that, you get x minus target, and that would be your gradient. Here, after doing all of this math, we end up at the exact same place, right? And the funny thing about this is, I mean, this is obviously the funny thing about this. The useful thing about this is that it makes this gradient computation extremely simple, right? All you need to do is just apply this softmax softmax activation function, and once you have applied the softmax activation function, your gradient is taking the gradient is simply is is as easy as just taking the difference between the softmax outputs and your one hot encoded uh, labels, right? Or it doesn't even have to be one hot encoded labels. It could be uh, any form of uh, probability distribution based uh, labels that you could use here, because at no point in this derivation have I used the fact that these labels are one hot encoded, right? This is a very generic result that appears out of this combination of softmax and cross entropy, right? You can apply it for all kinds of probability distribution output type problems, and it becomes the good thing is that the gradient computation is extremely simple, right? Then the next thing, of course, once you have the gradient with respect to the pre-activations, right? uh, Remember, we are going in the reverse direction, right? So we have computed gradient with respect to x2, and we computed gradient with respect to a2, right? Now we need to compute the update to w2, right? Which is go into this equation over here, and the update over w2 is a very simple problem once you have computed this gradient, right? Because essentially the function that you're applying is linear, right? Matrix multiplication, matrix vector products uh, are linear transformations. So when you take the gradient of the loss with respect to W2, it's nothing but uh, gradient of, it's nothing but the product of x1 of k and the gradient of a2 of l, right? And this takes a very general form that you can describe as a product of pre-weight activations and post-weight gradient, right? So x1 of k is the pre-weight activations, activation that is going into this weight multiplication, and gradient with respect to a to l is basically the gradient that appears after the weight, right? So it is gradient, so basically gradient over here multiplied by the activation over here will give you the gradient with respect to the weights, and just negative of this gradient is all that you need to update the values of the weights, right? Weight update happens in the negative gradient direction. So the key takeaway from all of this discussion is that chain rule is very important, right? Because this is essentially what is enabling all of this computation to happen, right? All of this gradient design to happen. And then finally come to the hidden layer, right? So we have done this, we have basically kind of done through this. So once we reach here, right, and this is a very simple function. Once we reach here, we'll have a way to compute the gradient for w1, and if we are able to compute the gradient for w1, that completely describes our problem, right? So that completely solves our problem, because we only have two sets of weights. We already know how to compute the gradients or how to compute the updates for w2. All that is remaining is w1, and for that all that we need is gradient of L with respect to a1, right? So we'll go step by step. First we'll compute gradient of loss with respect to x1, right, which is the post activation, and again we'll apply chain rule. We'll look at the gradient of loss with respect to a2, which is what we had previously computed, right? In the previous slide we had computed this first term, so I'll not repeat it again. I'll just keep it like that. And the new term that we have to compute is gradient of a2 with respect to x1, which is very simple, right? Because a2 and x1 are linked by a linear transformation, right? A2 is nothing but w2 times x1, so the gradient of that is nothing but w2, but because we are going in the reverse direction, we have to take a transpose, right? Because instead of going from x1 to a2, we are now coming from a2 towards x1, right? So we take transpose of the weight, w2 transpose, multiplied by this term gradient of L with respect to a2, which is what we had computed over here. So one thing to note here is that I have dropped the uh, index. I'm no longer considering like a2 of I or a2 of j, and the way you understand this is that I am treating the gradient, I'm considering the gradient of the entire vector at once, right? So gradient of L with respect to a2 is nothing but the vector containing the gradient of L with respect to a2i for all of the I that that are relevant for this, right? So it's the entire vector of the gradient, which is why I can do this matrix multiplication, right? So if this is a vector, this is a matrix, I can multiply them and I will get another vector, which is this vector, right? So I have gradient of loss with respect to x1, then I just need gradient of loss with respect to a1, and we'll be done, right? So we take gradient of loss with respect to x1. Again, we apply chain rule, gradient of loss with respect to x1 multiplied by gradient of x1 with respect to a1. So this is the term that we have computed here. This extra term is the gradient of the ReLU function, right? And ReLU function, like I described, looks like this, right? So it's 0 until 0, and then it becomes a linear, right? So it is a simplest nonlinear function that you can apply as a activation function. And the gradient of this is also very simple. Technically speaking, this function is not differentiable at 0, but the way we get around it, like we have previously discussed in earlier sessions, is that we simply define the gradient at this point to be 0 and just move on from there, right? So we don't deal with we don't really care about this kind of point non-differentiability conditions, right? Because we can simply define the gradient at that point, and that as long as that is like a meaningful choice, it will work, right? So the gradient basically looks like this. It is 0 for all the values less than 0, and it is 1 for all the values greater than 0. And the way that you uh, present this, simply you just write something like this, right? So you just write x1 greater than 0, which will give you exactly the gradient that you need. So with this, you will have gradient of L with respect to A1, and then for update to W1, right? We just replace, we just repeat this form, right? But with W1, A1 and X0 instead, right? So X0 and A1, X0, A1 and W1 were involved in this equation. This is the first equation. So now in the backward pass, it is the last equation that you deal with. So this A2 just becomes F1, uh, this W2 just becomes W1, and this X1 just becomes X0. And then you will have an update rule for W1, which is the first layer of first layer weights. And with that, the entire description of this neural network model is complete, right? And the good thing about this is that even though I just deal with a single hidden layer, uh, this uh, treatment is extendable to as many hidden layers as you want, right? Basically, what will happen is that this final computation will be repeated as many hidden for whatever number of hidden layers that you have. This final computation will be repeated. Obviously, output layer gradient will be just one computation that is that is the same. Hidden layer gradients will be just computed again and again, and then for every hidden layer, the corresponding weights you will just update them based on this equation, right? For which the terms you'll just get. So yeah, so I think that concludes today's session. If anyone has any questions, you can ask me. Yes. 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 Uh, yeah. So the condition I equals to j and other condition basically, right? So here you are computing the gradient with respect to a to I, right? So you are computing, if you look at this equation here, you're computing gradient of loss with respect to the ith element of a2. A2 is a vector, right? And here, because so we have to go through the steps, right? We cannot compute the gradient of we have, like, if we want to compute the gradient at the step of a2, then we have to go through the gradient at the step of x2, and then from x2 we have to come to a2, right? And here you will notice that I have written this as a sum, which basically is, which goes over all of the elements of x2, right? And you compute the gradient of those elements with respect to a2 of I, right? So here I have summation over j equals to 0 to n classes, and it goes gradient of loss with respect to x2 of j, right? So the jth element of the post activation, and then this post activation, gradient of this post activation x2 of j with respect to a2 of I, right? So this is the jth element of the post activation, the gradient of the jth element of the post activation with respect to the ith element of the pre-activation, right? So everything, all of these layers have a pre-activation and a post-activation, right? And because this softmax is a normalized function, right? The ith, the jth element of the post-activation, like, depends on every element of the pre-activation, right? The every element of the post-activation depends on every element of the pre-activation, essentially, because it comes up in the denominator, right? In the denominator, you get all of the elements of the pre-activation. You get the uh, the exponent of those things, right? And because of this connection, or rather because of this dependency, when you take the gradient with respect to some a2, right? You take the gradient with respect to some a to I, you have to be you have to also take into account the fact that, you know, x to j for j not equal to I, right? So those x to j's are also dependent on your a to I, right? Obviously, if j is equal to I, then, it is uh, a to I giving rise to x to I, which is a very straightforward, or rather very expected relation, right? Obviously, the same element, pre-activation of the same element will impact the pre-activation of the its own post-activation, right? But the thing here is that because the softmax is normalized, the pre-activation of every element impacts the post-activation of every element, right? So you have to compute the gradient with respect to all of the post activations. Only then will you get the proper gradient that you want with respect to the pre-activation, right? So here you can divide this into uh, two classes basically, and there are multiple ways to divide it, right? One of the ways to divide things in this gradient computation actually does actually deals with the fact that your output, or your target output, uh, is one hot encoded, so you can divide it in terms of this is the correct class and these are all all the other classes, and then you compute gradients like that. I have done it in a slightly different way. I have not used the uh, I have not used the added information that labels are one hot encoded, right? But even if you don't use it, it comes out to be the same, right? And yeah, and then you basically divide it. So this I equals to j case is basically the pre-activation impacting the post-activation of the same neuron, the same element, and I is not equal to j is basically pre-activation of some neuron impacting the post-activation of some other neuron, right? And this is when you take the gradient of them, you get slightly different results because one of these terms will become 0 for I not equal to j, and that's how you get this versus this, and then you apply a little bit of algebra, and you take advantage of the fact that summation of this label j's is always 1. You get this very clean, uh, very nice looking output, right? Which has direct parallels with uh, the MSE loss, right? But of course, they're completely different things. The good thing is that this is a very simple gradient to compute, right? So I hope that uh, clears it out. No, uh, both indices are for the same layer, right? So they are not for different layers. They are uh, not for pre or post activation, right? Pre-activation is denoted by A, so A2 is pre-activation. Post-activation is denoted by X, so X2 is post-activation, right? I and J is basically, I is what we are trying to compute for, right, over here, and J is the generic, right? So J is the summation over everything, and because this softmax function is normalized, right? uh, this thing, this denominator, right, makes it so that the post activation of any element in this softmax is dependent on the pre-activation of every element in that same layer, right? Because you're adding up all of these terms over here at the bottom. You're adding up all of these terms over here. No. I and j just represent the index of the neurons in the final output layer. Nothing else. Yes. Uh, no. See, J goes from 0 to n classes, right? So J is basically summation over all of the indices, right? And then I is one specific index within that, right? Right. No, so uh, you compute the gradient with respect to the weight, and in the negative direction of the gradient is where you do the weight update, right? So you compute gradient of you compute this gradient of L with respect to W2 L comma K, and then you apply a minus sign over here, and that is the update. So you write W2 equals W2 of L comma K equals W2 of L comma K minus some learning rate multiplied by this term, right? So that's what it means to be negative gradient direction. Okay. So I'll end the call.